Dr. Hao Cheng, scientist and engineer in the quantum information frontier, is currently an assistant professor at the Department of Electrical Engineering, Graduate Institute of Communication Engineering, National Taiwan University. Dr. Cheng received his bachelor's degree in the Department of Electrical Engineering, NTU. He received his PhD degree at the Graduate Institute of Communication Engineering, NTU, and at the Center of Quantum Software and Information, School of Software, University of Technology, Sydney. After receiving his PhD degree, Dr. Cheng joined the Department of Applied Mathematics and Theoretical Physics, University of Cambridge, as a postdoctoral research associate, and he also affiliated with the Darwin College. His research and scientific interests include quantum information processing, quantum communication, quantum machine learning, statistical signal processing, and matrix analysis. Let's all welcome our speaker.
Thanks, Lindro, for a very nice introduction. So I think everyone hear me very clearly, so I don't have to use the microphone. Okay, so today I will talk about this topic. This topic is kind of very long, but essentially I want to talk about the one-shot quantum information theory. And what's that? I will talk about this later. And this work can be found on arXiv. And I hope this talk, this is not the really official talk. I will take it as a short tutorial. So if you have any questions, please interrupt me anytime so you can follow my presentations. Okay, and I think most of you may not be very familiar with quantum information theory. So I will first talk about the rough idea of this area and what's going on in this field. So in general, quantum information theory, or we call it quantum Shannon theory, is to describe the transfer and processing of information using quantum systems as carriers of information. That's the rough definition. And we will mainly focus on the fundamental limit of quantum information theoretic tasks. And I will divide the development of this field into 4 stages. And the first one was initiated by von Neumann, Shannon, and Landau. And we already know that there's a von Neumann entropy. The concept of this entropy originated from von Neumann and also the Shannon entropy. And also Landau studied this entropy in the field of statistical physics and thermodynamics. So we'll call this the first stage of information theory, like this the birth of information theory. And around 70s, there are many researchers studied the optimal measurement for the problem of quantum state discrimination. I will talk about this problem later, by Holevo-Helstrom and Yuan Kennedy and Lux in 70s. At that time, but there are only just a few people study this field. And around 80s and 90s, lots of work are developed by Charles Bennett. They proposed the dense coding, teleportation. I guess that you already know. And also, they developed the Shannon theory in the classical case to the quantum case. So by many people, we call this the first order theory. They can describe the fundamental limit of several tasks. For example, like they derive the channel capacity for communication problems, and also the fundamental limit of compressing a data either in classical case or quantum case. So that's I call a third stage of the development. And at that time, they all consider the first order of quantum information task. I will talk about this later. And more importantly, they consider the asymptotic regime. That's the third stage. And then starting from 2009, by several researchers, firstly in the classical case by Poliansky, Fiesenpool, and Sergio Verdú in the Princeton, they made a lot progress on the one-shot information theory. And then by Masahito Hayashi and Makoto Mamhill, they extend their theory to the quantum case. So at the fourth stage, we're concerned about the one-shot quantum information theory and beyond. I will talk about this one-shot in the next slide. So that's my view of this development of the quantum information or quantum Shannon theory into 4 stages. And my research will mainly focus on this part, the one-shot quantum information theory. Okay, let's first review communications over quantum channels. We'll talk about quantum in the following, but when you describe like this communication, what are you communicating? You are communicating classical information or quantum information. So let's first talk about this classical communication. And this is the classical communication over a quantum channel. And the first order theories were developed by Holevo-Helstrom and Westmoreland. So this is called the famous HSW theorem. So let's see. So because now we want to communicate classical information, so we will use this as a message to describe the classical information. So for example, this m, small m is the message, is a random variable, and without loss of generality, we assume it's a uniform distribution in a set from 1, 2 to the m, capital M. We want to transmit such a classical message through a quantum channel. So how we want to do that? We'll first use an encoder, which is a map, to transmit each message to a density operator on some Hilbert space an. This an means that it's a tensor product of n. This tensor product of n Hilbert spaces. So it could be very large and is any integer. Okay, and then we'll send this density operator through a bunch of IID channels. For here, each n A to B is a CPTP map, and then it's from the density state space in the Hilbert space A to density operator space to the Hilbert space B. And then because now we consider the asymptotic region, so we will use a bunch of such channels independently. Each channel is has a tensor structure, so we call this IID channel. So the channel output will like this form. So it is very straightforward. At the end, we will use the decoding, which is actually a POVM, a quantum measurement, to measure this channel output state to get an estimate of the transmitted message. So we call this the classical communication through an IID quantum channels. And the capacity of this task was developed by this HSW theorem. So what is the capacity means? So if we define the communication rate R to be the asymptotic rate of this message size, we care about what's the number of bits per channel that you can send through this task. And we only will take this n to the infinity. So we define this as the communication rate. So if this rate is smaller than a so-called channel capacity, which depends on the channel, then this error, the probability of this error.
So the IID channel, 1 qubit channel, so that is
Yes.
1 by 1. So I just I send the qubits separately.
Jointly. Yeah.
It's like n is like n tensor n.
Exactly.
Joints.
Yes. Yes. Because here it's a tensor n, capital N tensor small n. So capital N tensor small n is also a channel, right? And it's from the space of HA tensor n to the space of B tensor n. So it's very large on the input space and also on the output space. So we call it, we use this channel parallelly. Yeah. So that's the IID setting. But yes. Yes. That's a very great question. So actually, this rule depends on small n, the transmitted message. This density operator can be entangled across a bunch of those ID channels. Yes, it can be entangled, and also the channel output can be entangled across all of the Hilbert space. Yes, in general we can do that because we can use an entangled encoder to do that, and then we will use a entangled decoder to get our message. So yes, that's possible. And usually we will have to do that to get a good result. Okay. Otherwise, if we use a product encoding, then there's no the performance will not be very good. Okay. And yes.
So like this rho n is like, say there is a 3-qubit entangled state.
Yes.
So I send through this ID channel. So it's like maybe I just use like one. I have 3 qubits, and each one I send it out to with maybe one fiber into the other place. Like is it like that? And then I don't know,
like in this case, it depends on that if at least rho m is entangled or not. If it is product, okay, so this an, for example, let's define this as a1 m tensor rho a2 m and you can send this each of the states through a fiber. Okay, so that's one of the coding scheme. But also you can send an entangled states, and you send each subsystem through an optical fiber. So that's also doable. We call this an entangled input. So that's more powerful because you have correlation between these.
each fiber is just
A subsystem. Exactly. Yeah. Each is A to B. You can send a very large entangled state. But you already noticed that to do this, it will be very difficult in practice because you have to prepare very large entangled input state, and also at the channel output, this decoder has to be very large, right? Because you have to if each channel is a qubit channel, but you have a bunch of these qubit channels, or for example, like 1,000, then you have to use a 1,000 qubit quantum processor to do a decoding, right? So that's actually very difficult in practice. Okay, let's get back to this channel capacity problem. So this as the communication rate is smaller than channel capacity, then this error will goes to 0 as n goes to infinity. That's the HSW theorem. Okay, so that's why this channel capacity is important. However, this theorem holds in the asymptotic regime, meaning that this result is true as n goes to infinity. So that's mathematically it's true, but practically it's very hard to do that because you have essentially have to use an infinitely large quantum processor to do the decoding. Okay. So that's why we'll switch to the one-shot case. But let me talk about the quantum communication first, and then we'll then consider the one-shot case. Okay. The second is the quantum communication over quantum channels. In this case, we are not transmitting a classical message, but we are transmitting an arbitrary quantum state through a quantum channel. So again, we'll use an encoder to encode this quantum state, arbitrary quantum state, to another possible any entangled very large quantum state, and then we'll send this through an IID channels. So the channel outputs is like this, and then we also use a decoding. But here, this decoding may not be a measurement because we want to reproduce such a quantum state. So this may be say this is sigma. Then we want to reproduce a sigma head such that this sigma head is very close to sigma with high fidelity, for example. So that's the quantum communication. So I want to mention that you have to pay attention to what's the information you want to transmit through these quantum channels, and all of these are in the IID sense. So the difficulties are in the practice because you have to use very large decoding to do that. So in the fourth stage of the development of quantum information theory, we usually care about the one-shot setting, meaning that we only use the channel once instead of IID. Then we care about how well we can do such communication tasks. That's the main goal of the fourth stage. Okay, so that's the one-shot quantum information theory. This means that the quantum channel, previously, the quantum channel we are using is like this tensor n, but now the quantum channel in one-shot quantum information theory does not have specific structures. For example, like this ID, we'll take this whole thing as just an arbitrary n. So we will not use it repeatedly. So I think that's more understandable. So that's the illustration of the classical communication of a one-shot quantum channel. Here we only use a channel once. So I think that's more intuitive. Okay, and in this work, we will mainly focus on this scenario, classical communication over a one-shot quantum channel. Okay, so there are two questions for this task. The first one is that for if we want to transmit this message with size capital M, which is an arbitrary integer, then how small is the decoding error? Here I define this epsilon star as the probability of the decoding error, this m hat not equal to m, and then but actually this probability depends on the encoder and also the decoder, right? Because if you use very bad encoding and decoding, then the error will be very large. But we care about the minimum error over all possible encoding and decoding. Encoding here is we call a CQ map, and this decoding is a QC map, and that's actually a POVM or quantum measurement. So we care about how small can this minimum error be. So that's the first question. And on the other hand, we can ask another question. Given that this optimal or minimum error is at most some epsilon in 0 and 1, then how large is the message size of capital M that we can transmit through this quantum channel with error at most epsilon? That's the second question we want to ask. Okay, and normally we'll if we take log on this M, that's the number of bit, we call this quantity as the epsilon one-shot capacity of this channel, classical communication of this channel. So that's the number of bit you can achieve an epsilon error communication. Okay, and we'll obtain some bounds on this quantity. Okay, so that's the two questions in this one-shot quantum information theory. So for now, are there any questions? I hope I describe the question very clearly, so you know what's going on, and then I'll go into some existing works.
So one shot?
Yes.
You mean it's like
Just one.
Yeah, but I mean if I have 3 qubits, then I just 3 qubits go to the same channel.
Okay, so first we have to fix the channel or fix the optical fiber, and then you may ask, then what's the dimension of this HA and also the output Hilbert space. So, for example, if the input space is only 1 qubit, then you can only encode your message to a 1 qubit state and send through it. Yeah, but we only use channel once, and this channel can be arbitrary, and also it could be even infinitely dimensional. So we didn't put any restrictions on our channel. That's the one-shot setting. Yes.
Question 2, do you need to specify the possible distribution?
Of what?
Log n.
Distribution of log n?
No, I mean the density matrix sample from some distribution. Otherwise, how do you define the log n? I mean, if you are going to compare with capacity, summation over some possible distribution over the matrix tree.
Okay, here we will assume that this message is uniform from 1 to capital M. 1, 2 to the capital M. So that's all we will consider. We want to care about how large is the message, or how large is the equiprobable message that we can transmit through this channel with error at most epsilon. Of course, we can, and that's more involved. But if we can do this uniform, then by Shannon actually has we call that a source channel separation theorem. Okay, so that's actually a great question. So Minjian asked a question that if we have an arbitrary source which is described by some probability distribution, okay, then how can we do this one-shot communication? First, we can compress this to some uniform distribution. For example, M in 1, 3. This can be done by some classical compression. And actually in classical communication or in classical information theory, we call that the source coding theorem. And then we can use this channel coding at the end. Okay, so we can do this separately. And we will actually, we don't have, Shannon proved that at least in the classical case, he proved a source channel separation theorem that the channel capacity will not be, it's the same. You can separately optimize your source coding and channel coding, then we will not lose too much channel capacity.
The statement is in the classical case is the optimal scheme can be done by separately optimize
The channel capacity is the same.
Is there theorem about separate?
That's a good question. So for CQ channels, for this kind of CQ channels, the answer is yes. That's been proved. Yeah. And the intuition is that the first part is actually classical. It's not content.
For the classical capacity case.
Yes.
But for quantum information, you say that there's no.
That's a good question. For the quantum case, people always consider that jointly, because let me go back to these slides. Here, I didn't specify this quantum state to be a maximally mixed state. It can be arbitrary sigma. So that's more like a
this domain, they always do the job
jointly. Yes. And that's a very good question. And but actually people know there's a separation, but in a quantum case, we want to transmit arbitrary quantum state. So we'll do that jointly. But we can also transmit, for example, like a maximally mixed state, and that's a very a more specialized case. And in many cases,
the distribution is embedded in the
exactly.
State.
Yeah. This is a special case. Okay. Yeah, I can talk about more on this, but I'll continue to my talk. But we can discuss this later. Okay, so I hope you understand these two questions very well.
So for message size n.
Yes.
But what does this size mean? Like
This.
Each time I only send one number. It's right.
Yeah.
Okay. So this size is because.
For example,
like how I can encode it. So
this capital M can be some like the T bit, and you want to send like more large message through a channel, right? And if you can send much more bits, then your communication rate will be high, because if you look at your phone, the number is like the bits per second. Like in 5G, you like your transmission rate is like like gigahertz, right? So giga means that you can transmit many bits per second. So that's the message size.
the size is 3 per second. How many bits I can send?
It's a bit. It's the number of bits to the exponential to the bit. Actually, it's up to a log, but because we want to send as large as message as possible, right, to the channel. It means that we can send many bits of information. Because what's the entropy of this message? It's log m. So if we can transmit large message size, then it means that we can transmit more information through this channel. Okay. So let's continue. So, but here I want to make some remarks on these two one-shot information theory and also the classical communication, also quantum communication. So the modern approach to this quantum communication of quantum channels is called the decoupling method. I will not talk about this, but there are some nice papers discuss this. As for classical, let me talk about this quantum communication first. So here I will only consider that the message to be transmitted is like a completely mixed state. And then if we purify this completely mixed state, it will be a maximally entangled state between some system M and R. It's just the purification. Then we will send this M part through the encoder and the channel to the end. But the reference system, or the purification part of this state, will go through here. Then we want to make our channel, our decoding output to reproduce this maximally entangled state as the original one. That's the goal of quantum communication. In other words, we want to preserve the entanglement of our source all the way. However, there's a quantum channel here, and if you know there's a Stein-Spring dilation of this quantum channel. So for every n from A to B, we can make it to some B and E environment by some isometry. This is called Stein-Spring dilation. So there's some information leakages to the environment. So here, this information leakage to the environment may be entangled to this reference system R. In that case, you will no longer get a maximally entangled state, because due to the monogamy, if your message and head, your reproduced message is maximally entangled to the reference system, then it is independent to any other systems. That's according to the monogamy. So the decoupling method is actually very intuitive. The goal is to decouple this environment of what we call the complementary channel to this R. We want this R to be decoupled from this E, so that this R will be maximally entangled with M hat. That's our goal. So that's why we want to do decoupling. That's the main idea of this decoupling. It's very intuitive. So the modern approach to this quantum communication is through this decoupling method. If you are more interested in this topic, you can see a Dupuis PhD thesis. However, for classical communication over quantum channels, the modern approach is based on the so-called information spectrum method. It's different from the decoupling method. So people may ask why, and also this question haunts me for quite a long time. So there's a basic question: can we apply the decoupling method to analyze classical communication over quantum channels? And why we want to do that is because in quantum information theory, there are many tasks: communication, compression, and so many other tasks you will see later in this talk. Then for each task, we have one method. For the other task, we have another method. Can we somehow unify all of these methods in a more unified, simple framework? That's a fundamental question. Can we apply this decoupling method to the scenario of classical communication of quantum channels? That's a question that I want to ask, and I will address this question at the end of this talk. The answer is yes and no. Okay. So let's talk about existing works on this one-shot quantum information theory. This is a general recipe for doing one-shot quantum information theory. Again, I will not assuming any specific structures on the state or channel. They may not be ID. Okay, so the general quantum information theoretic task, we will reduce it to a quantum hypothesis testing task. I will talk about this later. That's a general recipe. And then at this moment, this quantum hypothesis testing has been well studied. So there are many one-shot characterizations of this quantum hypothesis testing divergence. For example, the relative entropy, I think you already know that. There are other quantities to describe this. For example, we call it hypothesis testing divergence between rho and sigma, and also there are information spectrum densities. There are the quantum Renyi divergence between LAN, the Pace version or sandwich version, and there are also the we call it smooth entropy. There are many characterizations in this part. Then you may ask, then how exactly do we reduce this information theoretic task to a hypothesis testing problem? So that's the main thing. Actually, it's still ad hoc in this field, and For quantum communication, or we call the fully quantum case, the decoupling method is like a main approach. But for classical communication, there's so many methods, so it's not unified. And some approaches are tight, some approaches are not tight. So it means that if you can find a good or tight analysis or reduction to the quantum hypothesis testing, and you are done. So that's the general recipe. But the difficult part is in the second stage, how to reduce an arbitrary quantum information theoretic task to a hypothesis testing problem. That's the main questions. Okay, so a powerful method is called the information spectrum method. So let's first consider this more specialized channel we call the classical quantum channel, which sends any classical symbols to output a density operator on some Hilbert space B. Okay, so the goal is again to transmit a message which is a uniform distribution in this set 1, 2 to the capital M. Then we will use some encoder. An encoder can be described by some code book, which is a one-to-one correspondence between your message and your code word. You map each message to some symbol, some code word, because the secure channel takes any symbols to a density operator, and then you apply a P of n to extract your message and pay it. Okay, and this method was done by Hayashi and Nagaoka 20 years ago in this paper, and they derived this operator inequality for any operator A whose eigenvalue between 0 and 1, and every positive semi-definite operator, this equality holds. Operator inequality holds. And here I use a definition of the non-commutative quotient. A divided by B means that we take the B to the minus in half and to multiply them on both sides of A. Okay, because due to non-commutativity, it's not easy to define the quotient, so we will adopt this symmetric quotient all the way in this talk. Okay, actually this inequality is ugly, and it depends on some constant C. This constant could be arbitrary large. So you may ask, what does this mean? The answer is it's actually not easy to answer this question, and I believe that nowadays many people in this field also don't understand this inequality very well. So that's the problem. Somehow this inequality, this method works, but people don't really understand why this method works. But it works. So we can write papers, we can produce some works, but to the bottom we don't understand this very clearly why this works. Okay, and how to prove this? Actually, in this paper, they prove this inequality, but you can see this proof is very this highly non-trivial, and it's not easy. So at least to me, when I teach students about this, it's a big problem. It's very hard for students to understand why this works and how to apply this in quantum information theory. Okay, so but in 2009, there's some progress, and
Could you explain?
A is an operator in 0 and 1, in 0 and identity actually.
But I don't know like how it related to the classical quantum channel holding.
That's the thing. It's not easy to see how to apply this inequality to. It's just like different animals. That's the thing. Yeah. So somehow it works, but people don't understand why it works. That's how I want to simplify it. Yeah, you agree, right?
Yeah, but then I don't know like how it works. This scenario.
That's a good question. You can see this paper, but actually I don't want to do this again, because now in this work I have more simpler method, so we can totally forget about this. Okay. But in 2009, by Oscar Mancini and Mark Wieldy, they published a paper called Union Bound for Quantum Information Processing. And you see this theorem, you don't have to read every details, but you can see there are some funny coefficients similar to the Hayashi-Nagaoka operator inequality. So what's this? The union bound means that if you have a classical probability distribution and some event, then we know that this is just a basic result in probability course, right? We call this a union bound. and you don't know how to prove this. And you can rewrite this by De Morgan's rule. So you can also consider the intersection of event, and it can be upper bounded by, for example, like the probability of A complement plus the. So this is just a way to rewrite the union bound. So here they want to do such kind of things. Each P1, P2 to the PL is like an event. Then they want to bound this union bound into a quantum setting. So it's actually a nice result. So how they do that? They kind of to modify Hayashi-Nagaoka operator inequality to come out with this quantum union bound. But and then they can apply this quantum union bound with some techniques by Mark Wilde. They call sequential decoding and with some probe systems. They can obtain the same result as using this Hayashi-Nagaoka operator inequality. So at least we understand a bit more. So the Hayashi-Nagaoka operator inequality plays a role like a union bound. So that's actually a good observation. However, to prove this quantum union bound is actually also non-trivial. It is also very hard, at least to me. Okay, so that's the existing works. So the goal of this work is to provide a conceptually simple and intuitive proof by directly using the critical measurement. I will talk about this critical measurement later. So we will propose actually a novel analyzed method to this classical communication of quantum channels. It turns out we accidentally we get a tighter one-shot bounds than all of the existing works, and we also this simple proof can be extended to all the quantum information processing tasks in a streamlined way. Okay, so let's see the proposed method. Okay, before that, we'll talk about this quantum state discrimination. This is our starting point. So in the second stage of quantum information theory, Holevo-Helstrom studied this quantum state discrimination problem. Let's talk about this binary case, the binary hypothesis testing case. We'll use these words, quantum state discrimination or hypothesis testing, interchangeably. So we can flip a coin, 0 or 1. The head is 0. The button is 1, for example. And then for each 0 and 1, we'll produce a quantum state to describe your system with some prior probability P0 and P1. That's a binary hypothesis. Then we'll apply a measurement to distinguish this system to decide it's 0 or 1. Okay, for this measurement, it's a 2 outcome measurement. So this T is a test, and then this T in favors of row 0, and then I minus T in favors of row 1. We'll use to discriminate row 0 and row 1, and we define this optimal error as the decoding error is formed like this. So I think you can understand this formula. That's just the definition of this minimum error of quantum state discrimination. Okay, and Holevo and Helstrom obtained a corresponding expression for this optimization problem. And I think you already know this formula in your quantum information and computation tasks. It's expressed by this 1/2 minus the trace distance between row 0 times P0 minus the row 1 times P1. Okay, that's our starting point. I will take this as an arbitrary operator A and take this as an operator B, and we'll use another notation to describe this quantum state discrimination. And then I will use this idea to the general channel coding problem. Okay, so this is the main course of this talk. First, I will define this we call the non-commutative minimum, which is defined by given any 2 operators A and B. Right now you can assume they are positive semi-definite. Then we consider the lower bound to A and B, or the Hermitian operator smaller than A and B, and then we take the one with the maximum trace. So it can be viewed as like a greatest lower bound. So we call this the minimum. Okay. we define this guy as the one with the largest, greatest trace. Okay, Holevo and Helstrom in 70s actually proved that this quantity is unique. It's unique. This maximum can be uniquely attained, and then it's given by this formula: 1/2 times 1 plus b minus the absolute difference between A and B. So if you take trace of this guy, you will see, and also use the fact that this guy is just the one known. Then this produce this the Holevo-Helstrom theorem. Okay, so that's their result, and I will use this notation all the way throughout this talk. Okay, and they also show that this has an infinite representation, and this formula is just like before for the binary quantum state discrimination. Okay, so how do you interpret this guy? This quantity is called the minimum error of discrimination between operator A and operator B. And if you are uncomfortable about this, you can take this A as the, for example, the scaled density operator P0 times rho 0, and this B as, for example, P1 times rho 1. But this A and B can be arbitrary positive operators. So back in 70s, Holevo and Helstrom studied this problem in a very general scenario. They consider even infinite dimensional operators or even to the von Neumann algebra. Okay, when this trace A plus B equal to 1 is normalized, then this error is actually the error probability. But this interpretation is very general. It applies to any Bayesian setting, so you can call this a minimum error or minimum loss or minimum cost or minimum Bayesian risk, anything. Okay, so it is interpreted as the minimum error for discrimination between A and B. I will use this throughout this talk. Okay. Any question at this point? And it's actually not introduced by me, it's by Holevo and Helstrom in their papers in 70s, and also Helstrom's book. And there's a very nice paper by Odinat and Milan Mossoni to derive many properties of this non-commutative minimum, and also they also study the non-commutative maximum. Okay, let's look at some basic properties of this non-commutative minimum. We will use this later. First is this Holevo-Helstrom theorem, the corresponding expression, and uniqueness of this quantity that we know. Second, it's increasing under the partial order. So for every A prime larger than A, B prime larger than B, then the trace will increase. And this can be seen directly from the definition itself, from this definition. So I will now prove it. It's very, very simple, just by definition. Okay, second, it's monotone increasing under any trace preserving map. And why is that? Because if you take trace and then there's a one known on this minus one known, right? And if you read the Nielsen and John's book in chapter 9, they already proved that this one known is contractive under any trace preserving map. So it's an intact book, and there's a minus here. So when you take any quantum channels on your states A and B, then the trace increases, and that's a basic result. Monotone under trace preserving maps. Okay, it's also a jointly concave map. Why is that? It's because of the one known, because the one known is a known, it satisfies the triangle inequality, right? So it's convex, and there's a minus in front of the one known. So overall, it's a concave function. It's also very simple by the definition by the properties of the known. Okay, you also satisfy some direct sum structure, and if you are not familiar with this, let me mention that if you have a direct sum with B, you take one known. This guy is just the sum of the known of this A and B. So you can just use this to see they satisfy the direct sum structure. Okay, and then that's more involved. There's an upper bound to this quantity by this trace A to the power 1 minus S, and oh sorry, there's a typo here. This should be a times a to the 1 minus power times b to the s. This is times, okay? And for every s in 0 and 1, this inequality is called the quantum channel bound and was proved by Ordinance et al. in 2008. And actually, this inequality is not trivial at all. And many researchers has tried to prove this inequality back in 2000s. This is upper bound. Then there's a lower bound to this trace of the non-commutative minimum by this guy. A times the A plus B to the inverse 1/2 times B to this guy. It satisfies this lower bound. And why this lower bound is true, I will not go into the detail, but I will provide you some intuition why this is true. And actually, this result has been proved in one of my papers last year. Okay, let's see the commuting case. Oh, this A is just some scalar A and B is just some scalar B. Then we take the minimum between the scalars, and this guy is lower bounded by this quantity. Sometimes we call it the parallel sum or something. And it's trivial to see this inequality is true. So this lower bound is just like a quantum or matrix version of this classical inequality. Okay, that's the first intuition why this is true. And let's see a second spatial case. If this A and B have equal trace, for example, they are density operators, so they have unit trace, then the Bonin and Keneal theorem proved in 2003 or 2, they show that using a critical measurement for quantum state discrimination, then the error of using critical measurement is at most twice of the optimal error. And this is a very well-known result. If you are not familiar with this, you can see the John Waiter's book. There's a nice proof for this Bonin and Keneal theorem. So let's see. So we use this critical measurement. What's a critical measurement? If we want to discriminate between rho and sigma, and you want to design your test will be chosen as this rho over rho plus sigma. The I minus t is just the sigma, and rho plus sigma. We call this the critical measurement. It means that we are in favor of our state, which is proportional to the density. Proportional to the density over the sum of the states. That's the definition of critical measurement. So let's see the error probability of this using this critical measurement. The rho times this, because right now we want to calculate the error. So this rho calculate times the I minus t, sigma times t, and t is this guy. So you can see this very easily. Okay, and then by the cyclic property of trace, this critical measurement error is like this. Okay, so it's just the lower bound. Okay, and by Bonin and Keneal theorem, this error is at most twice of the optimal error. Then what's the optimal error? By Holevo and Helstrom theorem, the optimal error is the trace of the non-commutative minimum between these two states, and there's a prior probability 1/2 for each if we consider equiprobable case. So this optimal error is 1/2 times this trace of the non-commutative minimum. We just put this back into the Bonin and Keneal theorem. We will see that this guy, the trace of the parallel sum, is smaller than this trace of the non-commutative minimum. So in other words, this lower bound can be interpreted as an adaptation of the Bonin and Keneal theorem. It relates the performance of using a critical measurement back to the optimal one. That's the intuition behind this lower bound. Okay, and actually you can prove this by adapting Bonin and Keneal theorem. They are a well-known result, and you can see my paper to this. And actually, in this paper, I provide a more strengthened inequality to this quantity. Okay, let's start our proof. Our main result is the one-shot achievability bound for classical quantum channel coding, and it can be applied to the general classical communication of quantum channels. So this is the statement of the theorem. For any classical quantum channel which maps the classical symbol to any density operators, it can be even infinitely dimensional. I didn't assume any structure on this channel. Then there exists an epsilon code, which means that we want to transmit, we can transmit an equiprobable message with message size n, capital M, and then the optimum error, the probability of the decoding error is smaller than epsilon. There exists such an decoding that we can transmit this M and with error at most epsilon, such that the following equation holds. This error will be upper bounded by this guy. The trace of the rho xb. What is rho xb? Rho xb is the CQ state, and this p rho b given x is the channel output, and this px is any probability that we use in the random code book. This holds for any px. So from this equation, you can already smell the mutual information, because the mutual information between x and b is given by the relative entropy between the joint state against its decoupled. So from this expression, you already have sense why the mutual information will play a very important role in channel capacity, because we have this. Okay, second, if m goes large, then the error, the upper bound will become also large. It means that it's a trade-off between the error and message. If you want to transmit more message, then your error will also will be larger. Okay, that's the theorem, our main theorem. And there's no other like previously there are some C or C inverse constant. There's no longer those constants. Okay, so let me prove this result. I will only use this slide to prove this result. Actually, the proof is a 3-line proof. Okay, so given any code book of x1, x2 to xm, this means that we make each small m message to some code word xm. Then the channel output will be what? Will be rho b xm, right? This is a CQ channel. Then the channel output will be rho b xm. Then we use this channel output to form a pretty good measurement. Now it's by definition it looks like this. Which will decide x proportional to the density of this to its density, and the denominator is the sum of other states with all of other x in this code word. Okay, we'll use this pretty good measurement to decode our message. Okay, so first, for transmitting each code word in the code book, we want to relate our error using this PGM to this non-commutative minimum. So this is the error probability of transmitting symbol x, and then we will, because it's an error decision, so we times identity minus the pretty good measurement. Okay, so you just calculate this, and by simple manipulation, you can see that this guy equals to is an equality. It's equal to a trace of this rho bx. Rho bx is the channel output that we transmitted. And this I minus the pretty good measurement is like this. The denominator is the sum of all densities, but I intentionally write this sum as the rho x and the other part, and the numerator is the sum of the other part. It's just by simple algebra. Okay, if you take the blue part as an operator A, the red part as the operator B, you will see this guy appeared before. So we just use the lower bound of this non-commutative minimum. We can obtain this A, B, and this is non-commutative minimum. Okay, so we get this. We got obtain this first inequality, first upper bound. Actually, this is done. We can. This is a result. You can take this as the error estimate. But usually we will use a random code book. So this is any code book, but actually we'll use a random code book, meaning that for each message, we will choose a symbol xm according to some probability. For example, xm. We call this a random code book. And why we want to use random code book, I will explain this later. So actually, each symbol is random. means that each channel output is random. So in the end, we need to take expectation over those random code choices. So here, this x is random variable. Those x bar are all random variables. So we need to take expectation. Okay, we'll first take this expectation over x, and then the expectation over x, all of the x bar condition of x is report. Then we want to take this expectation inside of the non-commutative minimum. And as I mentioned before, this non-commutative minimum after trace is jointly concave. So we can move this inside to get another upper bound. Okay, so here I put this conditional expectation inside. Then by linearity, you can change the order of the sum and the expectation. Then what's this guy? The expectation of the density operators. By the okay, so here this x is not equal to x bar. Then we will use the pairwise independent code book. So this expectation can be viewed as taking expectation over x bar. Then taking expectation over x bar on this guy, this is just the rho b, the average state or the marginal state of a CQ state. If we define this rho xb, then this x bar has a probability distribution px. Then the marginal of this, if you trace out the x bar, x part, then you get this average state, the rho b as the marginal state. So this random code book actually simplifies our problem to get this rho bx, and then there's how many sum in this? There are n-1 such rho b here. So this is our main result. Okay, so we are done. We only use two inequalities to get this quantity, and then by the direct sum structure, you can move. Okay, you can express this averaging into a direct sum structure. So in the end, it means like it's a non-commutative minimum between rho xb, the joint state, and it's decoupled, and there are n-1 many decoupled. So we are done. So it's a very simple three-line proof to this problem. Okay, so let me illustrate all of these things again using some pictures. So at the channel output, you have many states to discriminate. Okay, so assume that you are transmitting this message x1. So the corresponding density is the blue part, and then you apply some POVM element, and we choose this pregram measurement. We call this pi x1. This decide x1. Then the other part is the wrong decision, the identity minus pi x1, and it is like this. So by a closed loop, this multiple quantum state discrimination using pregram measurement is like a binary discrimination between the left part and the right part. The left part is just one state. We can call this blue part the A. The right part is the sum of the other states. We call this the B. So this pregram measurement can be write as this one, A over A plus B, and the right part is like this one is like B over A plus B. So it becomes a binary hypothesis testing between A and B. Okay, so that's the idea. We call this the one versus the rest classification strategy. Actually, has been used in statistics or machine learning. So that's our techniques. But using pregram measurement is suboptimal. So the next is to relate it to the optimal measurement. So we relate it to this non-commutative minimum. So it becomes the optimal discrimination between the yes.
I just wonder, how do I know I'm choosing like pi x1? I can choose pi x2.
For which? For what?
I mean, like, so now it's like we want to know whether it's rho x1, right? So after the channel, it gives you some output, then you want to know whether it's rho b x1. But I mean, but you can only know whether it is x1. If it is not, then how you have to do it again to with another pi, like pi s2b.
Okay, so by definition, what's the error? for this quantum state discrimination problem. The error is the sum according to Bond rule, rho bx times I just write this as the according to the definition. So when we take this, I interpret this guy as the error probability of so this just from definition of this error probability, right? From Bond's rule, the error probability is the trace of this guy rho bx times the other part, and the correct decision is rho b times pi bx. So this means that this pi bx is this guy, then it's in favor of decide this x1.
Yeah, but I mean, like, then if it's not x1, then
Like this, the other part, the rest.
yes.
So with the error probability is to decide the rest of the states.
So the rule is not to say up to the output state is like, I don't know, to decide whether it's x1 or x2 or x4.
No, it means that you will decide this x with probability this. Right, that's Bond rule. You have a bunch of states and you apply a measurement, then you will decide x with this probability.
I think the test is to just out x1 and not all of them.
You can sum of them later. Here I just pick x1 and you will sum each of them. Here is a sum of all other.
This question is here is only picking x1.
Yeah. For example, or you can pick any other. In the end, you sum of them.
If F1 follows some distribution and what?
We will take expectation later in these slides. Okay, so here I assume you understand this binary discrimination. Then it's an optimal discrimination between this rho b x1, and then in the end you can sum over x all of the x. Okay, so you will get this non-commutative minimum. Okay, but actually you are done. But this right-hand side, this red part can be very messy because this code book can be arbitrary. So x1, x2, x3 to the xm they can be arbitrary. So this sum can also be arbitrary. So we will take expectation. That's why we use the random code book. Then we take conditional expectation to because each density are random states, so we take expectation on all of them. All of them becomes rho b. So you can see why random corpus helps, because the right hand side is no longer the sum of a bunch of states. They are all the same, equal to rho b, because we use this expectation. Okay, but here this x1 is also random, so in the end we'll take this expectation of x1. So this picture means that you randomly draw a state and then you compare it with n-1 many rho b, the marginal states. So that's the idea. And then in the end, you can express this by the direct sum structure. You are comparing the joint state against the marginal of it. Then there are n-1 many marginal. So you obtain this upper bound. Okay, I think I will have no time, so let me close this talk in 10 minutes. Okay, so forgive me, I will take too long to explain, but I will end this in 10 minutes. So this guy, okay, so let's recall what is this mean. The trace of a commutative minimum with B. This means that the minimum error of discrimination between A and B. So this yellow part means that the error of a classical channel coding problem is upper bounded by the minimum of discriminating the joint state between input and output and n-1 many rho x tensor rho b. So that's the interpretation of this bound. Okay, you may wonder what's the application of this bound. So there are some implications. First, if you use the upper bound for this non-commutative minimum, you will directly obtain an exponential upper bound to the error probability. So this exponent is defined by some Renyi divergence. I will not go into detail, but it already appeared in some existing works. And by comparison to existing one-shot exponential bonds, firstly, Bonachev and Holevo in 1998, they studied the pure state classical quantum channels. They obtained similar exponential bond, but their bond has this additional constant 2 in their result. And in Hayashi's one of Hayashi's papers, he considered general CQ state, and he has this constant 4. So in some regimes, their bond is trivialized because the error probability will be larger than 1. Okay, and by applying my the moderate deviation techniques in my previous papers, so we can extend this result to the moderate deviation regime. I will talk about this later. Secondly, by using the infimum representation of this non-commutative minimum, we can get a expression in terms of the hypothesis testing divergence, the lower bound to the message side. So the message side can be at least such thing, and this gives the tightest one-shot capacity bound so far. So because by comparison to the previous results, they have the larger, like higher order terms, and also so this bond is tighter than all of the previous bonds. Okay, so let me use this picture to illustrate the implication. So this is the bond I got, the one-shot bond. By directly use the quantum channel bond, we get a exponential upper bound. And when we apply this bond to the ID channels, then use the additivity of the Renyi divergence, we will get this exponential decay. We call this a large diffusion regime, and this holds for any n. By using my techniques previously, when the rate, communication rate, approaches the mutual information by some speed an, is vanishing, but not fast than 1 for square root n. Then the error will still vanish sub-exponentially. We call this a moderate diffusion regime. And also, this bond implies the one-shot capacity by the following the lower bound. Then by using the second order expansion of this hypothesis testing divergence, we will get a small diffusion regime. So you can see this mutual information in the first order, and then the second order is by this square root n. And also by method in Marco's book, Marco's paper, we'll get this moderate diffusion regime. The left side is the only one-shot bonds. The right-hand side is only ID asymptotics. It means that the proposed one-shot bonds can unify all of the moderate and small diffusion regimes, and all the result comes from this one. So it means like at least this bond can derive all of the existing result, and it's tighter. Okay, let me use this chart to illustrate. So the x-axis is the communication rate, the y-axis is the error, and this bar is the channel capacity. And if you use the channel once in a one-shot case, you may get some error like this. And it's not very good because you use channel only once. If you use channel many times, like n is equal to 5, then you'll get sharper result. Then the large diffusion means that when the rate is smaller than channel capacity, then you get this exponential decay. This epsilon, this error converges to 0 exponentially fast when the rate is constant away from the channel capacity. But if the rate is converged to the channel capacity at a speed of 1 over square root n, then this epsilon will be a constant. We call this yellow part the small diffusion regime. And the moderate diffusion regime means that if the rate converges to the channel capacities by the speed not faster than 1 over square root n, then the epsilon, the error, will also goes to 0. That's the big picture of all of the ID asymptotic characterizations. Okay, and this result can be easily extended to the classical communication of a general quantum channel. Previously, we only consider the CQ channel, but here it applies to the quantum channel as well. Okay, here I want to mention that this result, I use a second order expansion of the hypothesis testing by Curry's paper. And then actually I have a conjecture that I didn't solve. If you are interested, you can think about this question. I conjecture that this second order expansion can be improved to this guy. The lower bound could be tighter by this 1/2 log n. If this is true, then with my one-shot bonds, it will give the best possible achievable third order coding rate. We will give this result. It's an ID result, but I do believe that this is true. And if this is true, then we can imply this result. Then this is the best possible third order coding rate for general channels, because for some classical channel, this this third order, the third order is like is log n, but the log n is actually the log n plot times 0. This guy cannot be improved because there are some classical channel that is optimal for this rate. So if this is true, then we can get this third order coding rate result. Then it's the best possible if you don't have any assumptions. Okay, so if you are interested, you can try to solve this conjecture. Okay, so let's go back to the general recipe of the one-shot quantum information theory. Here I propose a reduction, and it seems that this reduction is tight. And now the bottleneck is not about this reduction; it's in the higher order characterization of quantum hypothesis testing. So this method actually is tighter than the existing quantum hypothesis testing. Now it becomes the higher order analysis for hypothesis testing is actually the bottleneck, not the reduction. Okay, and I will have no time, but this method applies to the entanglement-assisted case. So additional to the usual classical communication, you share an entanglement between your encoder and your decoder. In this case, the simple method also applied here, and we'll get a similar achievability bound for this entanglement-assisted classical communication. It also gives the tightest one-shot capacity for this scenario. And I will have no time to go through the proof, but you can check my paper. It follows exactly the same way to get this result. Okay, so here is a summary of my result. I formulate this problem into a one-shot quantum packing lemma. It's like this form. And by using this result, we can extend this result to many other existing quantum information theoretic tasks. For example, the broadcast channel. Now we want to transmit message MB, MC to Bob and to Charlie, and they will apply their decoding quantum measurement separately. Then we will obtain a tight achievability bound for the error for Bob and for Charlie. And also for entanglement-assisted broadcast channels, we will have this entangle between encoder and Bob, and also entanglement between encoder and Charlie, and then we'll obtain similar achievability bound for broadcast channels. And for multiple access channel, now that Alice and Bob, they want to use the channel simultaneously, then Charlie will aims to decode Alice's message and Bob's message. We can also obtain an achievability bound for this multiple access channel. And if they have entanglement assistance, then we can also use the same idea to get a result. So actually, the proposed method is versatile for many tasks. Also, it applies to classical data compression with quantum science information. Here, we want to compress a classical source, which has a general probability distribution. We want to compress it to some index set. Then we want to apply a decoder to get it. But here we have some quantum science information as a helper to decode our result. Then we can also obtain a simple and elegant achievability result for classical data compression and quantum science information. And actually, in my paper, I proved a stronger result by this. So this is a more stronger one. By using this, I can get a more tightened achievability bound. But this is ugly. I don't like this. So this it's tighter. I just mentioned this. I can get this result. And I will not go to this detail. The techniques is based on the data processing incurred. Okay. So in conclusion, let me get back to the question. Do we unify the decoupling method to classical communication over quantum channels? No, actually, our method is nothing like decoupling. But now I actually understand this more. So right now, I will divide many quantum information theoretic tasks into two categories. The first one I call the packing type problems, because we know that the infinite dimension case, the channel capacity is finite. Then we can send like D dimension can send D messages through this channel because they can become orthogonal, so we can perfectly discriminate them. If we want to send more messages, then there are some overlaps, so there are some errors. So it's like the goal of channel coding is to make the codes as far as possible. So it's like a packing problem. So I call this packing type problems. So communication type problems, the compression type problems with quantum science information, we call this the packing type problems, and also all of the multi-user network setting. They are packing type problems. So in this work, we improve this basic one-shot packing techniques. And there are other problems I call the covering type problems: the quantum self-covering, convex splitting, quantum channel simulation, and privacy amplification, and also decoupling. I call them a covering type problem. What's the covering type problems? If we have an ensemble of quantum states, for example, like this, then we'll get a mean of these states. Then the mean of state can be like, for example, we assume it has force pole. Then we randomly draw some realization, rho x2, rho x3, and then we mixture them. We take a mixture of all of the ensemble average. And in one of my paper last year with Li Gao, we show that this ensemble average will approach this empirical average will approach the ensemble average strongly in norm. So we call this the covering type problems, and they are all related in some sense. So actually, I cannot use I didn't use the decoupling to solve the packing type problem, but I proposed a new packing type problems for the left side. And there are other problems. They are mixture of these packing type and covering type problems. For example, like the private communication over Y-type channels. You want to transmit your message to Bob, but you want to prevent your information leakage to the if. You will use packing type tool to transmit your message to Bob, but you will use covering type techniques to prevent your information leakage to the if. Then the quantum communication is like a more advanced generalization of private communication over web-type channel. So actually, quantum communication is more involved. It requires the packing type problems and covering type problems. So in my recent goals in 1 or 2 years, I want to improve all of these packing type technique and the covering type techniques, and hopefully I want to sharpen all of the existing results for all of the quantum information theoretic tasks. Okay, so I've already run out of time. Let me get to the conclusion. So we provide a conceptually simpler and intuitive proof for achievability, and it can be it's tighter than existing results, and it can be applied to many packing type problems in quantum information theory. And any other applications of this result, I do believe that if we want to use measurement and you want to use random code books, then maybe I do believe that this analysis can be applied. Okay, for bounding message size, we get the tightest achievable one-shot capacity bounds, and I think in the ideal case, it will achieve the best possible third-order coding rate. For bounding error, actually, it has some room for improvement because it does not yet achieve the tightest error exponent yet. So I do believe that there's some improvement. Okay, so I will stop here, and if you have any question, please let me know, or we can discuss it offline. Okay, sorry for the delay. Please stop. Okay.
That's okay. That was a great talk. Thank you very much for coming here. Let's all.
Any question from the online audience?
I think not.
Yes, Mingyan, please.
Some question, but I just ask one question here.
Yes.
And I think the result is very interesting and good. And it seems that your main result is for general distribution, right? So in your introduction, you say it's from uniform distribution.
Yes.
So it seems more general. Is that the case?
No. I only consider the uniform equiprobable message. So the message is uniform in capital 1, 2, and as I mentioned before, if you consider any source, then you can always use the classical source coding to compress it to a uniform distribution. So, but that's only classical part. So.
Transfer the message and into
Random code books. Yes, it's arbitrary. Arbitrary.
So why don't you just think and as arbitrary?
Oh, it's different. Actually, it's different because what Minjun talked about is this. Let me go back to my main results. It's for this the choice of a random code book. So here in my main result, holds for any probability distribution px. This px is for a random code book, not a message. And we can optimize this px. So that's the channel capacity, because if you remember the channel capacity, and you need to optimize this px. but my result holds for any px, so you have the degree of freedom to optimize this further. Yeah, but this probability is for a random code book, not for a message.
Do we have any more questions here? I think not, so let's end here.
Okay, thank you very much. Okay, so